Okay, so now we'll see a little bit about modeling with symmetric nets. And up to this point, you have seen symmetric nets, the formal syntax, the enabling conditions, the firing rule, and we are going to see more detailed examples that will give you a better feeling for what you can model and what it is. Let's take this example of a train problem where you have N1 trains that are distributed on a circular track, and this track is decomposed, as you can see here, here, into different sections. So let's assume that you have N1 trains and N2 sections, and of course you don't want your system to induce crashes between trains, so they will run all along these tracks. But for security reasons, we'll have a train enter a section only if it's empty. So this train, for example, can go there only if there's no train there, otherwise they collide. And also if there's no train on the following section, so that's here for this train. So as to ensure a distance between trains and they have time to brake or things like that. Okay, so we have to check that the next section where you want to go is free and the section afterwards is free as well. So let's model that with a symmetric net. What are the color domains that we'll have in this example? So the first color domain is I need to express what a train is, so I will have a set of trains. So this is C1 here. This is that contains trains TR1 to TRN1. And then we have sections also to model, and they will be numbered as well. So I have a second set, C2, which contains the sections SC1 to SCN2. In the architecture of our net, we'll have places and transitions. So the places will give the state of our systems, so the state of trains and sections. We can have a train on sections, so there will be an association between a train and a section here, and that will lead to a place that we will name TRSC for a train on a section. So this will express the fact that a particular train is present on a particular section. Well, then you have the information on the sections that are occupied. But you want to check as well that some sections are free. Therefore, we'll have another place which we'll call SC avail for available, sections available, and that will contain all numbers of sections that are available. The transition will model the progress of a train, so taking a train from one section to the next section where it wants to move. So let's connect that all that together in the net. So you can see here the two places, train on a section, section available, and their associated colors. So the train on the section contains a train and the section it's traveling on. So therefore it has a color C1 cross C2. So C1 is the set of trains, C2 the set of sections. So a pair, train and section. As concerns the sections available here, the color set is C2 because it contains just section identifiers. Now the transition here in the middle, transition T, it has a color C1 cross C2 because it will take a train on a section and it will manipulate both of these elements. For the arcs, you can see that you have arcs going from both places to the transition and back from the transition to each of the places. What will happen is that we have to take a train that is on a section and to update the fact that the train will be on the next section afterwards. And we also have to take the to check that the sections are available and free eventually, the next section. So what we'll do when we want to find this transition, we'll train T on the section S here. So this is the train that I want to move from section S to the next section. And then we'll check that the next section, so it's S++ here, is available. And we said we want to look ahead, so we have the next section. So S++++. So we have to take these two and check they are available. If it is the case, then we will move the train. So the train will move from its section S to section S++. So it will free section S here, and it will return it to the set of available sections. And it will put back this token S++++, which was the look ahead, just to check that two sections further it was free as well. And also we'll put the train on section S++. So the train occupying this section will move from section S to section S++. Okay, so that is one way to model this problem. Another possibility is to say I don't want to have these kind of writings because it starts cluttering the net, and I want to use some other features of nets, and I have guards that are available. So here you can see you have a guard saying y equals S++, and instead of using S++ in the arc labels, I use y everywhere, here and there and there. Right. So that is another possibility. I take a train T on the section S, and then I will have to check for the transition that y equals S++, and I will take the sections y and y++ to verify they are available, and the rest is similar. Okay, so at this stage, you know how to model something using symmetric nets. You have seen a comprehensive, detailed example, and what we want to do with nets is generally model a system and analyze it. So we'll see in the next sequence how the reachability graph can be built in order to perform some analysis on this model.